Owen's a Flames fan, which is good because when Calgary plays Minnesota tonight at the Saddledome, Calgary's going to win. But Minnesota's a pretty good team. This year, Minnesota Wild are 32, 11, and 5. That means that they have 32 wins, 11 losses, 3 times the number of wins than they have losses, almost at least, and then 5 overtime losses, which they get a point out of. In the last 10 games, they're 8-2 and 0. That means they have 8 wins, 2 losses, and 0 overtime losses. That's pretty good. You see a train barreling down the tracks here. You can tell it's moving because it's got that smoke coming out of it, right? What do these two things have in common? The Minnesota Wild hockey team and then this train that's barreling down the tracks. Okay, they are both working efficiently, yes. That's not where I'm going with this, but they are. If they're both working efficiently, they're both kind of hard to stop. Both kind of hard to stop, right? It's not impossible to stop them. You can stop a train. You can stop a good hockey team. But they're hard to stop, right? How hard it is to stop something, we often associate a word with that. And that word is momentum. Now, in the first one, we're talking about the momentum of a hockey team, how hard it is to stop a hockey team. That's psychological, right? It's pure psychology. You come up against a good hockey team, and a lot of times you get intimidated by that good hockey team, and you end up losing, so then they have even more momentum. It's even harder to stop them. But there's nothing physical about it oftentimes. It's just pure psychology. Whereas a train, it is physically difficult to stop a train. Right? There's nothing psychological about that. Your mind can be in completely the right place. You stand in front of that train, try to stop it, it's going to be pretty hard to stop that train, no matter how strong you are. We're going to talk about physical momentum in this unit, of course, how hard it is to stop something physically. Now, can you tell me, please, what might influence how hard it is to stop that train? What factor or factors influence how hard it is to stop anything physical? Give me one. Yep. Weight or mass. Mass, yeah. It's hard to stop something that is heavier, that has more mass. Mass is one factor that affects how hard it is to stop something. What's another one? Huh? Speed or velocity? Yeah. The faster something's moving, the harder it is to stop something as well. In fact, we define momentum as how hard it is to stop something. Notice they put it in quotation marks, because that's not really any kind of official definition. That's just kind of how we understand it and how we remember the official definition, which is the product of an object's mass and velocity. It's related, as two people just told me, to mass and velocity, and the actual value of momentum is equal to the product of mass and velocity. In other words, mass times velocity. Now, this is a term we learned about in Physics 20 that's similar to momentum. In fact, sometimes in Physics 20, you may have even used the term momentum interchangeably with this term. They're not the same thing, but they're close. Physics 20, we didn't really pay a whole lot of attention to the difference, but in Physics 30, it's important. There's a subtle difference, but an important difference between these two terms. You know what other term I'm talking about? It's a lot like momentum. Hamish? No? Good idea, though. August? Inertia, yeah. You guys remember from Physics 20 what inertia was? Okay, you're almost there. You're almost there. The tendency of an object to basically keep doing what it's doing. So if it's at rest, it wants to stay at rest. If it's in motion, it wants to stay in motion, right? So it's a tendency to resist a change in motion. The tendency to resist a change in motion. Now, how is that different than momentum? Well, momentum is a specific form almost. It's how hard it is to stop something. Inertia could also be how hard it is to stop something, but it could also be how hard it is to start something or speed something up or slow something down. It's how hard it is to change whatever it's doing right now, not just stop something. So sometimes an object has momentum and inertia. Sometimes an object just has inertia. Inertia depends on one thing only, and that is mass. Whereas momentum depends upon two things, mass and velocity. Two pictures up on the board, each of a train. What's the difference between these two situations? Yep. Good. One's at rest and one is moving. We got two terms that we just learned about. One is inertia. We didn't just learn about inertia because we learned about that last year, right? The other is momentum, which we did just learn about really for the first time. I want to identify which one or ones, diagram 1, diagram 2, have inertia and which diagram or diagrams have momentum. Let's look at inertia first. Does this train that's moving have inertia? Does it have a tendency to keep doing what it's doing? Does it have a tendency to resist a change in motion, can we? Yes, it does. It's moving and it wants to keep moving. It doesn't want to speed up or slow down or stop. It can, but it doesn't want to. It has a tendency to resist that. What about that train at the station? Does it have inertia? Does it have a tendency to keep doing what it's doing? Emma? Yes. It's at rest and it wants to stay at rest. So they both have inertia. What about momentum? The one on the right here, the one that's moving down the tracks. Does it have momentum? Is it difficult to stop? Yeah. What about the one that's at rest in the station? Does it have momentum? Does it have a tendency, or does it have a tendency to resist stopping? Is it hard to stop the train that's at rest in the station? No, it's already stopped. It doesn't have any momentum. So you can see how the two are related, inertia and momentum, but they're not the same thing. Okay, inertia is dependent upon one thing, and that's mass only. Momentum is dependent upon two things, mass and velocity. All right, I want to refer you to your data sheet here right now. The left-hand side of your equation portion of your data sheet, I want you to scroll down here under momentum and energy to where we're going to find an equation for momentum. Momentum is given by the symbol P. That's a lowercase p. A capital P would be power. And although we're going to see power a little bit in Physics 30, that's not what we're talking about right now. So it's a lowercase p, and you can see that it's equal to mass times velocity. Versus, I want to draw your attention to another one that you've seen before in Physics 20, Ek is equal to 1/2 mv squared. Similar equations, right? Both have m and v in it. What's Ek? Yeah, it's kinetic energy, good. Besides the obvious, besides the fact that the kinetic energy equation has a 1/2 in there and a squared in there, besides that, what's different about these two equations? What do you notice here that is different between momentum and kinetic energy besides the half and the squared? Yep. Yeah. Okay, so besides, yeah, that's right. Besides the actual quantities, momentum and kinetic energy, what else is different about them? Emma? Good. Momentum has velocity, which means momentum is a vector. Yeah, momentum is a vector. And kinetic energy has speed, which means kinetic energy is a scalar, right? So that means that if you ever have to find the total momentum of two or three objects, you've got to pay attention to signs, right? You got to pay attention to positives and negatives. If something is to the right and something else is to the left, then one of them is going to have a positive momentum, one of them is going to have a negative momentum. When you go to add those up, You got to pay attention to positives and negatives. But for kinetic energy, because speed is a scalar and kinetic energy is a scalar, there is no direction associated with kinetic energy. So therefore, even if one object is moving to the right and one object is moving to the left, they'd both be positive. This is the real focus of this unit, right? P is equal to m times v, momentum. That's what our unit is, momentum and impulse. But we see kinetic energy sometimes too, and we just want to recognize that it's a little bit different, not only in the equation, but in the vector nature versus momentum. All right, what do you think the units for momentum would be? We know it's a vector. We know that there's got to be a positive or negative associated with it. What about the units? M is in, probably going to be kilograms, right? V is in, probably going to be meters per second. Units would be kilograms times meters per second. That's kind of a strange set of units, kilograms times meters per second, but it is what it is. All right, I want to do the first example that's on the example handout that I gave you a few minutes ago. This one says a 145 gram baseball is traveling to the west with a velocity of 90 kilometers per hour. What's the momentum of the baseball? Watch carefully what I'm about to do. I have a blue pen in my hand right now because that's usually what I write with. I like blue. I'm going to put it down and I'm going to pick up red for a second here. I don't usually solve a problem in red. I'm picking up red here so that I can circle one or more things to draw attention to. I want to draw attention to things that I think that I may mess up on. Some silly little thing that's going to cause me to make a stupid mistake on a test. One of those things, you know, when you get your test back and it's like, I can't believe I did that. Are you kidding me? I understand this completely, and I made this silly little mistake. I'm going to pick up my red pen and draw attention to things that will prevent me, hopefully at least, from making those silly little mistakes. What's one of the things in this question that you think I want to circle to avoid making a silly mistake? Yep. Grams, yeah. If you're in chemistry, you probably want to stick with grams, but in physics, we want to be in kilograms. Now, circling it red doesn't guarantee you're going to remember to convert it, right? But there's a much better chance you'll remember if you're drawing attention to it by circling it red or highlighting it or starring it or something, right, to draw attention to it. Can we? Absolutely. Kilometers per hour. We want to be meters per second. Anything else here? Emma? Yeah, I got the west here as well. Now, because this is a pretty straightforward question where there's only one object going in one direction, the west is a little less important this time than if there was two objects, one going east, one going west, and so on. But it's a good habit to get into still. You got something that's west, usually make that negative, right? So it's probably a good idea to circle west so that we remember to do that, even in a question that's relatively simple like this one. Okay, let's write down some givens here. We got a mass of 145 grams, which if we convert that to kilograms, it would be 0.145 kilograms. Divide by 1,000. That's on your data sheet, by the way. It tells you the kilo is 10 to the 3, or 1,000. We have a velocity here of, well, we want to convert this to meters per second, right? Physics 20, I taught my Physics 20 students to multiply by 1,000 and divide by 3,600. There's a shortcut, though. Anybody learn the shortcut last year? You wouldn't if you were in my class, but if you were in Mr. Cordera's class, you might have. I'm not sure. Multiply by 1,000, divide by 3,600 is exactly the same thing as dividing by 3.6. Divide by 3.6. You can do that, and it works every single time. We want to find the momentum of the baseball. So let's say P is equal to M times V. The mass here is 0.145 kilograms, and the velocity is 25.0 meters per second. Do a little bit of math here, and our answer works out to be 3.63, 3 digits. 3.63, what were the units again? Don't remember? That's okay. Figure it out. What are the units? This is kilograms. This is meters per second. We're multiplying the two of them together, so it's going to be kilograms times meters per second. Oh, but wait. Yeah. I almost missed it myself. One person mentioned it here just now. We got to either make this west or make this negative, one of the two. Why did I catch that myself? Okay, why did some of you notice that? Probably because we circled west here and drew attention to that, right? We're less likely to miss that. Okay, maybe we go through the whole question, then we realize, oh wait, we forgot that. Oh man, I almost got a 0 to 1 on that multiple choice question because of a silly mistake, but I didn't because I circled west. At the very end of the question, I caught it because of the red circle that drew attention to it. All right, I'd like to take a look at worksheet number 1, please. There's 8 questions on that worksheet. For now, I want you to do questions 1, 2, 3, and 4, which are all based on the example question that we just did. All right, if you're having no trouble with those 4 questions, let's do another example that'll allow us to finish off that worksheet. This one says a 1.5 kilogram object falls from rest from a height of 14 meters down to ground level. What's the momentum of the object as it hits the ground? What's similar about this question versus the last example we did? Joshua?
It has a mass.
Yeah. Yeah, and we're gonna use that mass to find momentum, right? We're looking for momentum, just like we were in the last question. But what are we missing in this question that we didn't have in the last question? Yeah, we don't have the velocity. So you either got to find a completely different way of solving it, and I don't know what another way of solving it, like some completely other new equation that we haven't seen, or you got to find velocity somehow. Let's write down some givens, and then let's worry about how we're going to find velocity, and then how we're going to complete that to find the momentum here. We got a mass of 1.5 kilograms. We have, what do you want to call this 14 meters? Height, or what else could you call it? Distance or displacement? In fact, I'm going to call it displacement. I'm going to make it negative 14.0 meters. Right, because the displacement ends up being downwards. Anything else we have here? We read between the lines. Is there anything else we have? Yeah. Okay, VI is 0. Good. Yeah, that's important. Something else, though, too. Reading between the lines. Go ahead, Joshua. Yep. Yep. And that's going to be negative 9.81. Good. And what are we looking for here? We're looking for PF, the final momentum, right after it falls. There is different momentum along the way here, right? There's 0 momentum at the top, and then there's something at the bottom, and then there's changes as it falls. We're looking specifically for the final momentum, which of course is going to be equal to the mass times the final velocity. But we don't know what the final velocity is. So how are we going to find that? Suggestion. There's a couple ways that I can think of right now. One way is almost always what you guys tell me, though. What I would do. Good. So VF squared is equal to VI squared plus 2AD. And somebody already told me that VI was 0. So let's solve for VF by saying it's the square root of 2 times A times delta D. That's the square root of 2 times negative 9.81 times the displacement of negative 14. Solve for VF there. When we do, it works out, I think, to be 16.5735. Use the unrounded number, 4 or 5 decimal places. Let's multiply them now. 1.5 kilograms times 16.5735 meters per second. Get a final answer of 25 to 2 significant digits, it's 25 meters per second. There's a little bit of a problem here, though. It's subtle, and it's important. There are much bigger mistakes that we could make, for sure, but there is a small, subtle mistake here. You spot what it is? Joshua? What do you mean? Yep. No, I found the momentum, right? I found the velocity, and then I multiplied it by mass to get the momentum. Yeah, that's it, 25. Yeah, Reese. Oh, the units are wrong, actually. Yeah, that's not what I meant, but thank you for spotting that. 25 kilograms meters per second, you're correct. Meters per second would be velocity, right? Thank you. That's not what I meant, but that's still important. Hamish? Yeah, the direction. What did I solve for right here? The 16 meters per second. What is VF? No, it's not final velocity. That's the thing. It's not final velocity. What's VF? Final. What's not above the V? This is final, Hannah? Yeah, that's final speed, right? This equation finds me speed, not velocity. So this is the final speed. That's okay, because I know that it's moving downward, and I know, therefore, that I can put a negative in there to make it a velocity, right? I just changed the speed into a velocity. And that means that my final momentum will be negative 25 kilograms meters per second instead of positive. Or I could have written 25 down. I could have used the word downwards, right? All right, what I'd like you to do now is take a look at the last 4 questions for worksheet number 1. These 4 questions, I think you're going to find, are a little bit trickier than the first 4 questions, especially as you go further. 5 and 6 are much like the example we just did. 6 and 7 are kind of like it, but you got to think a little bit more on 6 and 7 as well. This is your homework tonight, in addition to the survey that I asked you to fill out earlier. You have about 7 or 8 minutes left in class to schedule it up. Maybe even get it done before you go home tonight. Just make sure this is done before class tomorrow.